So chapter 10, we are learning moment of inertia. Moment of inertia is something that you're going to use in mechanics and materials over and over again. It's something that you need to be able to calculate for any cross-sectional area so that we can use it for mechanics and materials. There could be a lot of confusion in this because you've heard the term before, moment of inertia. But there's two moment of inertias. And we want to make sure that you are familiar with those two and know the difference between them. So maybe in the past you've calculated what's called the first moment of inertia. That's called the mass moment of inertia, or often just the moment of inertia. Okay, and that one is related to how quickly something will accelerate when it's rolling. Okay? We do a whole bunch on that in dynamics. So if you're taking dynamics next quarter, we're going to do mass moment of inertia. Actually, one of our projects is based off the mass moment of inertia. But that's not what we're doing here. Here we're preparing for mechanics and materials. Mechanics and materials uses the second moment of inertia. So the first one measured the body's resistance to angular acceleration. How hard is it to make this thing spin? Okay? The second one is related to the resistance of a beam in bending. So this is directly related to bending moment. So we now know how to do bending moment by using our shear and bending moment diagrams. And then we have to figure out the moment of inertia to see what that actually does to the internal stresses of a beam. You can see that the equations are very similar, and that's why they're both called moment of inertia. The first one uses an integral over the mass, whereas the second is an integral over the area. So the second one is really a measure of how much stuff there is away from a neutral axis. The moment of inertia is a measurement of how much stuff, where the stuff is located relative to that neutral axis. You notice this y squared. It's going to take either the x squared or the y squared, that's the distance from that neutral axis in the x or y direction, and square it, and we take the integral of that multiplied by each little piece of area. Here's a better picture of that. The area moment of inertia is used to predict the resistance of a beam to bending. So how much will this beam bend? This is if you're designing a house and you wanted to know what size beam am I going to use in the ceiling so I can hold up the roof and the snow that goes in the roof and all of that stuff. So you'd have to determine what type of beam you need. And in order to figure that out, you need to know how it will resist bending. You can see a picture of an I-beam here, and the neutral axis that I talked about would be this axis right in the middle, the x-axis. The stress in a beam, which we haven't really talked about too much, but you learn about stress in mechanics and materials. Stress is force over area. So far, we've just been studying force. But if you think of all of your bridges, what we really care about is how much stress there is in each one of these members. It should be intuitive that a larger member could hold more force, and a smaller member can hold less force, right? So if we just look at the force, we're not learning a whole lot. If we look at the force divided by the cross-sectional area, that's telling us how much that beam is feeling stressed. So stress is really the measurement of whether this thing is going to fail or not. There are two types of stress. There's axial stress, which is something in tension or compression, like the bridges that you're designing. And then there's bending stress. Bending stress comes from a bending moment. So all of those shear and bending moment diagrams we've been doing, that's this M right here. The whole reason we're learning that is so we can put that M in this equation. And when we calculate bending stress, we're going to do My over I. M is the moment in the beam at that particular point. Y is over here on this diagram. It's the distance from the neutral axis. And I is area moment of inertia. Okay, now you're not really going to use this equation until mechanics and materials. We're not going to talk about stress, I'm trying to give you some foresight so that you understand why we are calculating moment of inertia. Right now we're just being introduced to moment of inertia so that we know how to calculate it once we get to mechanics and materials. So objectives: calculate the moment of inertia of an area using integration. Calculate the moment of inertia of a composite body by applying the parallel axis theorem. Hey, sounds familiar, right? That's just the same two things we did in Chapter 9, but instead of looking for x bar and y bar, which is a centroid, we're now looking for the area moment of inertia. And you can see that it's kind of related. The equation that we were using for x bar was the integral over the area of x times dA over the integral over the area dA. You can see this integral that we're using looks very similar to the top of that. Right? We just add another x. And that's going to give us the area moment of inertia. Basically what that's telling you is that in bending, it's more important how close the stuff is to the neutral axis. So the area moment of inertia. The equation is Ix, where x is telling you what moment of inertia you're finding. The moment of inertia about the x-axis would tend to be the moment of inertia that how this body resists bending about the x-axis. And then there's a moment of inertia about the y-axis, which it would resist bending about the y-axis. So Ix is going to be equal to the integral over the area of y squared dA, because y is the distance from the x-axis. Okay, so sometimes that can be a little confusing. You've got an x and a y in it, but it's just like what we did before when we were finding the moment. This is the second moment. Before, when we were finding the moment, we said that the moment about the x-axis was y times the force. The second moment is also y squared times the area. And Iy is going to be equal to the integral over the area of x squared dA. Okay? There's also a polar moment of inertia. The polar moment of inertia, we use a j to indicate. And the polar moment of inertia is the integral over the area of r squared dA. So the polar moment of inertia is actually the other two moment of inertias added together. Oh, I'm sorry. This book uses an I. Another book uses a J. I naught. And I naught is actually going to be equal to Ix plus Iy. That shouldn't be too confusing because we know that x squared plus y squared is going to be equal to r squared. Right? If we had this triangle right here, this would be x, this would be y, and that's r. So if we put integral over the area of x squared dA plus the integral over the area of y squared dA, that's going to be equal to the integral over the area of r squared dA. Just using the Pythagorean theorem. Procedure for calculating it is we're going to express a differential element, just like we were doing before, in terms of the coordinates describing the curve. So that's figuring out what your differential element looks like and figuring out the base and height of that rectangle, just like we did in the previous chapter. We're going to express moment arms for the centroid of the element in terms of the coordinates describing the curve. That's your x bar, your y bar, just like we've been doing. Substitute the formulations of the different elements for their centroids in the appropriate integral equation. Same thing. We're putting in the equation we're given. Express the function in terms of the same variable and then integrate. Let's go ahead and try one. So in this one, 10-2, we're just given the picture and we're told to find the moment of inertia about the y-axis. The moment of inertia about the y-axis is called Iy, and that is moment of inertia about y-axis. Okay, so the equation that we have for that is Iy is equal to x squared, the integral x squared dA. And we're going to do the same thing we've done before. We're going to find a differential element and draw it. I'm going to choose do vertical. So there's my vertical differential element, and I'm going to say the height is y, the width is dx, so my dA equals y dx, the integral over the area of x squared times dA, which is y dx. I'm going to put my limits of integration in the x direction because I have a dx, so it's going to be from 0 to 2. And you notice that this x that I'm putting in, this is not x bar. This is x. The x distance to each one of those variables. And then we just integrate. Integral from 0 to 2 of x squared times y, which is 0.25 x cubed dx, which equals integral from 0 to 2 of 0.25 x to the 5th dx. So then we just get x to the 6th over 6 times 4 from 0 to 2. 2.67 is the answer. What are my units? The moment of inertia of the area is meters to the 4th. Okay, I wanted to do this example too just to kind of show that it can be done in both directions. So in this one, we're given the picture and we're supposed to find Ix. Now Ix is going to be the moment of inertia from the x-axis, which is going to have y in it. So Ix is going to be equal to the integral over the area of y squared dA. Because that y squared is in there, we need to make sure that we use the right differential element. We need to use a differential element that is going to have that distance from the x-axis for each element we have, because it's in our integral. right? Which means we need to do a horizontal differential element. This is different from centroid. In centroid, we got to choose whichever one we wanted, and we would just calculate it. In moment of inertia, the reason that we could do that is because we would draw a picture and we would find the distance to, we would label the distance to the centroid in whatever terms made sense for our picture. Well, we can't do that in this case because the derivation of this equation has already been done. It's fairly complicated. You can go look in the textbook. We could rederive that equation each time if we wanted to do it with vertical. But most of the time it's just easier to keep that y in there and realize that y has to be the distance to each differential element from the axis. So if you're finding ix, you must use horizontal. And if you're finding iy, you must use vertical. Any questions about that? Okay, so I'm going to use a horizontal differential element. And we're going to do the same thing. Label the base times the height. The height is going to be dy. The base is going to be, that's good, 2 minus x. X would be this distance from here to here. So our dA equals 2 minus x dy. Y is equal to 0.25 x cubed. So that means that x is equal to 4y cube root. Okay, so now I'm going to say that Ix is equal to the integral over the area of y squared dA. I'm going to plug in my dA. My dA is, so that's going to be equal to the integral of y squared times 2 minus x dy. I have a dy here, so I don't want this x in here anymore, so I can perform the integration. So I got to substitute that in. So Ix is going to be equal to the integral from 0 to 2, because we're going in the y direction, of y squared times 2 minus 4y to the 1/3. Now it's just a little bit of algebra. It's a little ugly, but nothing we can't do. 4 to the 1/3, y to the 7/3, and perform that integration. Then we just plug in 2, and we get 0.533 meters to the 4th. And that's the measurement of how this particular system would resist bending.